Greetings, welcome to lecture number 9 on basic circuit theory. I am Razavi. Today we will continue to look at the principle of superposition and go over some examples of applying this idea to circuit analysis. And we'll see that when we have multiple inputs, multiple independent sources, we can simplify the analysis by superposition. And then we will go over two more theorems, Thevenin's theorem and Norton's theorem, that again help us simplify circuits and make them more manageable in terms of the mathematical labor that we need. But before we go there, let's take a look at what we covered in the last lecture. In the last lecture, we talked about mesh analysis. We said that just like node analysis, we can apply mesh analysis to a circuit. And the idea is that we identify all of the meshes in the circuit. A mesh is the smallest loop that we can find. And then to each of these meshes, we assign a current. For example, I1 is flowing through this mesh, I2 is flowing through this mesh. In the next step, we go ahead and write the voltage drop across every element in terms of the currents that we have assigned. So for example, R1 carries a current of I1 from left to right, thereby sustaining a voltage equal to I1 R1 with positive here, negative here. For resistors that carry two currents, for example this one, we have to pay careful attention. Okay, once we have the voltages written on the diagram, we go ahead and write 1 kVL per mesh. So we have a kVL around this loop, we have a kVL around this loop, around this mesh. So if we have n meshes, we also end up with n kVLs, and those allow us to find the n currents, and then the circuit is solved. One exception arises if we have a current source in the circuit. In node analysis, we remember that voltage sources gave us trouble. Here, current sources give us trouble. So the way we deal with this is that we say this current source is shared at most between two meshes, right? It cannot be more than that. So we take those two meshes and merge them into a larger mesh, which we call a super mesh. So now I have a mesh going like this, and it does not see the current source, so to speak. So I can go ahead and write a KVL around the super mesh, right? I can start from here and go around, add up all the voltages, and equate the result to 0. So that's one extra step that we need to take if we have a current source and we are performing mesh analysis. And then the other extra step is that because we have merged these two meshes and we have lost 1 kVL, we need to look for a KCL. And that KCL involves this current source and the currents in these two meshes. So I1, this current source, and this 2 satisfy KCL at this node. So that gives us one more equation that we can add, and now we have all the equations that we need. Okay, then we moved on to the principle of superposition. Superposition says that if we have a linear system that has multiple inputs, what we can do is we can find the output corresponding to each individual input and then add up all these outputs as the total result. The example I provided last time was my voice goes through this microphone and generates a voltage. If we have music, music goes through the microphone and generates a voltage. So it's natural to assume that if my voice and the music go through the microphone at the same time, the resulting voltage will be equal to the sum of the voltages that we obtain in those individual cases. So today we will go over superposition and its procedure and look at some examples of how we can use this idea to simplify circuits. Okay, but before we go there, I need to talk about two principles that we visited some time ago. I just wanted to refresh your memory. If I have a voltage source and I want this value to be 0, what does this correspond to? Well, that is equivalent to a short circuit, right? Because a short circuit guarantees the voltage difference between these two is 0. And so does this voltage source, right? It says the voltage source between these two is 0. Also, if you have a current source and we want its value to be 0, that is equivalent to an open circuit, because here no current can pass, and similarly here this wants the current between these two to be 0. So these are important ideas that we need to keep in mind as we go through superposition and Thevenin's and Norton's theorems. This and this must not be confused with one another. All right, so let's go ahead and look at the general superposition procedure. So superposition procedure. So I know what superposition means, and I have some sort of circuit or system, and it has multiple inputs. So for example, I have a voltage source here, and then maybe a current source here. So I have two inputs, and I have an output somewhere. It could be a current or voltage somewhere, anywhere you want. So let's say I have a voltage here, V out, and I would like to find V out resulting from both of these inputs. All right? Okay, so for example, call this V1 and call this I1. Now, we could solve this using node analysis or mesh analysis or any other principles we have known before, as long as we know KVL and KCL. But knowing superposition helps us because we have two inputs. Okay, so in the first step, we say keep input number 1 and kill all other inputs. Now remember, the word input from last time means an independent source. We always have to remember that, right? For dependent sources, we cannot do this. Only independent sources can be set to 0 or can be killed or can be considered in the superposition principle. All right, so for example, I'm going to keep this as is, and I'm going to kill this. Killing this means setting it to 0. How do I set this to 0? I go back here and I say for a current source to be 0, it has to be replaced by an open circuit. So I will take this out and I leave these two unconnected to make sure that I have an open circuit. All right? Okay. In the next step, we say let's go ahead and find the response at the wherever we want corresponding to this V1. So we say find response to input number 1 and call that something just to keep track of things. So V out 1. All right? Okay. Now we have found the output corresponding to one input. We will repeat this process now for other inputs. So repeat for each input. So for example, I set this to 0 and I consider this. This gives me some V out, and we'll call that, for example, V out 2, V out 3, etc. Right? Each of the sources, each of the independent sources will give us an output. And then finally, the final result will be the sum of all of these. So we say total response is equal to V out 1 plus V out 2, etc. Okay, so that's the basic idea. What we do need to remember are these two ideas, these two methods. So if I want to set this voltage source to 0, because I'm confining the response to I1, this voltage source has to be replaced by a short circuit. So I take it out and I short these two wires together. All right, so long as we know these, then the analysis is pretty simple. Okay, so with that, let's go ahead and look at some examples. So here's one example. Let's see what we have. All right, so let's start with something very simple. We have a voltage source here. We call V1. Then we have two resistors R1 and R2, and then we have a current source I1. And we want to find the quantity of interest to us is here, V out, and we'd like to solve the circuit. Or we could say, let's solve the circuit completely so that we find everything, all the responses. This could be one response, this current could be another response, this current could be another response, this voltage can be another response, etc., right? Okay, so I have only two independent sources here. I can use superposition as we just saw. All right, step number one, as we have here, we keep one input alive and kill all the others. So let's keep this one alive and let's kill this. Let's set it to 0. When this current source is set to 0, it has to be replaced by an open circuit. So we take it out and we just leave these floating, right, unconnected. All right, so you say keep V1. It's a good idea to redraw the circuit to avoid any confusion, at least as you begin to learn these things. Once you're good at them, then you can do it in your head. But at the beginning, you want to avoid mistakes, we just draw it like that. So the current source is replaced by an open circuit. So nothing is connected from here to here. So it's just that, right? And then this is the output. Okay, how much is the output? Well, this is a voltage divider. We have seen this a number of times. So I don't even need to solve the circuit. I can say that this output is equal to this resistor over the sum of these two resistors multiplied by V1. Right? This is what's called a voltage divider, as you saw before. So we say it's a voltage divider. And that means that V out, now I have to call this V out 1, just to keep track of all the outputs that I will end up with. So V out 1 is equal to the input V1 times R2 over R1 plus R2. So you can see that once we have these structures and they are built, voltage dividers, current dividers, etc., then every time we encounter them, we don't have to start from scratch. Yes, we could write node analysis or mesh analysis here, but we don't have to because this is already something that we have seen and we know the equation governing its behavior. Okay, so we found the output corresponding to V1. So we're done with these steps here. Now we go to the other input, with this one more input, this input. We set the previous input to 0, we keep this alive to see what happens. Okay, so we say keep I1. I have to set this to 0. How do I set the voltage source to 0? I replace it by a short circuit. So let's replace it by a short circuit, just like that. And then we have R1, then we have R2, then we have a current source I1, and then we have a new voltage. So I should call this V out 1, I should call this V out 2. So V out 2 is the output, is the response corresponding to the input I1. All right, can I write this right away? How much is V out 2? Well, R1 and R2 have a familiar connection. R1 and R2 are in parallel. Why? Because they share these two terminals and they share these two terminals, right? This is just a piece of wire. So R1 and R2 are parallel to each other. So then it's easy, right? I can just write it like this. So this is R1 in parallel with R2. And this is I1. And then this is V out. How much is V out? Well, we see that this current has to flow through this resistance. It has nowhere to go. So we see that the current of I1 is flowing this way. So is the output voltage equal to I1 times R1 in parallel with R2? No, it's equal to minus I1 times R1 in parallel with R2. Why? Because I1 is going this way. You see, it's going from top to bottom, from bottom to top. So the voltage takes a negative sign. If you don't like that, you can just say this current, you can say this voltage is also the same as this voltage, right? So then the current going from top to bottom will be V out 2 over this resistance, right? Going from top to bottom, you take the top voltage subtracted from the, we take the top voltage minus the bottom voltage, and that would be V out 2. So you can say that this current is V out 2 over R1 in parallel with R2. And then this current, if it's going this way, is opposite of I1. So that has to be minus I1. So in any case, we see that V out 2 is just equal to minus I1 times R1 R2 over R1 plus R2. All right, so now we have found both responses. We just add them up. When we are adding up the responses, we have to be careful about the polarities. So there's a negative sign here. We must remember that, right? Because each of these sources has some response. Okay, so we say V out total is equal to this voltage, which is resulting from V1. So V1 R2 over R1 plus R2. And then that voltage, which results from I1. So R1 R2 over R1 plus R2. So the circuit is solved. Now, is this manual labor less than if I had applied, for example, mesh analysis or node analysis? Not much. They're comparable. But sometimes superposition also gives us additional insights. For example, superposition can tell us which input has a stronger effect on the output. Here it's not that easy because we have a voltage and we have a current. We can't really compare a voltage with a current, but in any case, we can try to do that. It's always good to keep superposition in mind. As soon as you see a circuit with multiple inputs, that could be a nice shortcut to solve the circuit. All right, and I encourage you to ask yourself, now that we have a symbolic result, for example, if R2 goes to 0, this goes to 0. Why? If R1 goes to 0, this goes to 0. Why? Okay, try to intuitively explain these things. If R2 goes to infinity, this goes to 1 times V1. Why? Right? If you answer all these questions, then it means that you understand the circuit very well. Okay, let's see. All right, we'll go over one more example, which is a little more complicated, trying to apply superposition. So let's change the color of our pen here to maybe this color. Okay, so in this circuit we have several sources. We have 3 sources. So we have a current source we call I1, a resistor R1, then we have a voltage source V1, then we have another resistor here, another resistor here, another resistor here, and then we also have a current source up here. So call this I2, and then R2, R3, R4, and we are interested in this output here. So that's our output, V out. Okay. All right, so it's a circuit that has 3 independent sources, I1, I2, and V1. And the output of interest happens to be this voltage here, which we call V out. So we can apply node or mesh analysis, not a big deal. If you want to apply node analysis, this voltage source has to be treated along with these two nodes as a supernode. We can do that. But in any case, let's try to use superposition. All right, so as usual, we go and keep input number 1 and kill all the other inputs. Okay, so we say keep I1. So I1 is here. This has to be set to 0, I2. What does it mean? It has to be opened. So I have to take this out of here and leave these two wires unconnected. So it just becomes an open circuit. It goes out of the picture, right? This entire branch goes out of the picture because no current can flow through it. And then how about this voltage source? When we set a voltage source to 0, its value has to be a short circuit. So I take this out and just short these two nodes together. So now I can see that circuit is very simple, right? So here's what we get. We have I1, then we have R1. So this is gone, and this is a short circuit, so just a piece of wire. So we have a piece of wire, then we have R2, then we have R3, and then we have R4. And this is what you might call V out 1. All right. Okay. So we have V out 1 here, and we need to find it. How do I solve this circuit? Well, that probably needs some node analysis or something. We can try to apply some shortcuts based on our previous knowledge. We see that R1 and R2 are in parallel. That's great. We can just consider it as one resistor. And then we have a resistor here and a resistor here. So let's play a little game here. I'll try to do this slowly so that you can follow. Okay, so this is one resistor. So we call that RA. All right, two resistors in parallel. RA is equal to R1 times R2 divided by R1 plus R2. Okay, so this current is coming in this way. It sees this resistor between these two wires, and then it sees another resistor between these two wires. So equivalently, this is what we have. We have I1 now splitting between RA and then R3 plus R4. Is that okay? So I1 is coming in. It sees two branches, right? It sees RA going this way, and it sees that branch consisting of the series combination of R3, R4. So that's that branch. So I1 wants to split between these two. It's a current divider, and we know the equation for current drivers, right? Okay, current dividers. So we say that this current, we're interested in that current. So that current is given by what? That current is given by the input current times not this resistor, but this resistor, the other resistor. So we say that current is equal to I1 RA divided by the sum of this resistor and that resistor. So that would be RA plus R3 plus R4. So that's the current that flows through R3 and R4. All right? Okay. But we are interested in V out 1, right? Not this currents. So how much is V out 1 now that we have found these? So I'll give you 1 minute for this quiz. Your job is to find V out 1 now that we have solved the circuit up to this point. All right? All right, so what did you get? Okay, well, what we see is that this current is flowing through these resistors. So that's the one that we have found right here. This current goes through R3 and it goes through R4. So if I want to find this voltage, which happens to be the voltage across R4, Ohm's law says multiply the current flowing through R4 by R4. So I can say that Vout1 is simply equal to the current that I just found multiplied by R4. So it's I1 RA R4 divided by RA plus R3 plus R4. Okay, so that's Vout1. That's the voltage corresponding to the response from I1. That was easy, right? Okay, so again, knowing these simple structures, parallel combinations, series combinations, dividers, etc., is extremely helpful because we can just look at the circuit and by inspection try to write the equations. All right, so in the next step, we have to go and keep another input and kill all the others. So let's go ahead and, for example, keep I2, and we set these two to 0. All right, so let me change the color here. And so we go ahead, let's see, we go to red. Okay, so we say keep I2. All right, so you can see that we really have to redraw the circuit after we set the rest of the inputs to 0. Otherwise, it's really hard to just look at the circuit and try to figure out all these things. So we keep I2. All right, I2 is here. This one is set to 0. What does it mean? It's an open circuit. Open circuit means cut this out, keep these floating, don't connect them to each other, right? So that branch is completely gone because no current can flow through it. And then we have to set this to 0. When I set this to 0, what happens? Well, there's a short piece of wire here, just with the way we had it before, right? Between R2 and R1, remember? We had a piece of wire, so it's the same thing. Okay, so the circuit reduces to, let's see if I can draw it here. I can try to squeeze it here. So we have I2. I2 is over here. We have a piece of wire. And then we have R1 on this side. I1 is gone because it's an open circuit. And now we have R2, R3, and R4. So we have here R2, R3, and R4. And this is the voltage we're looking for, so we're going to call this Vout2. Okay. So always make sure you place these dots here. These are called solder dots, as if you were soldering something. And they are a great visual aid to make sure that we know which wire is connected to which wire. If you don't have them, oftentimes it's difficult to see. All right, so here's the circuit. And my job is to find Vout2 in response to I2. All right. Okay, so let's see what's going on here. That's interesting, isn't it? Okay, so what do we see here? It's a very peculiar case. I2 wants to flow through something. That's what a current source wants to do. And our understanding is that the current always prefers the path of least resistance. You have a current divider. The current that goes, the branch that carries most of the current is the one that has the least resistance. You can see that here, right? So if RA goes down, the current through the other one goes down. So the current through this one increases. All right, so if I have I2 and I have a piece of wire, and then I have some other stuff, which way would I2 want to flow? I2 prefers to flow through this wire here, right? It doesn't have anywhere else to go. Or, if we don't like that, we can think of it this way. this piece of wire guarantees that the voltage difference between here and here is 0, right? Okay, so this voltage difference from here to here is 0 volts. Is that okay? All right. So let's try to redraw the circuit a little bit so that these resistors have a more intuitive picture to them. So I have a 0 volt difference here, right? So let's try to do that like this. This is 0 volts plus minus. And then I'm just redrawing things this way. And then I have I2. Approximately, I'm turning the circuit around by 90 degrees. Okay. All right. And then I have R1. R1 is here. Then I have all of this here, right? So I have R2. These are connected. Then I have R3. And then I have R4. Do you agree that these are the same circuit? I just turned it around, turned it counterclockwise by 90 degrees. So far so good? Okay, so we see that the voltage difference between here and here is 0, right? Okay, so if the voltage difference is 0, how much is the current through this resistor and this resistor? Well, the voltage difference is 0, so the current through these is 0. And similarly, the current through this branch is 0. So you see what's happening is that this current source entirely flows through this little loop here, right? It has nowhere else to go because this is a piece of wire. This piece of wire guarantees a 0 difference between these two. As long as we have a 0 difference between these two, we cannot have any current here or here or here. So this current source has to entirely flow through this loop. So none of these resistors carries any current because, in a sense, this current source is shorted out. It doesn't make it to any other branch. And that means that, for example, the voltage across R4, this voltage, is 0. So in this particular case, Vout2 happens to be 0. Okay, so we say Vout2 is equal to 0. So again, my objective is to analyze the circuits intuitively. If you don't want that, you can always write a bunch of node equations here, node analysis, for example, to see what you get, right? So, for example, call this ground, and then this is one node, VL2. This is another node, VA. These are shorted, so that's just one node. So write equations for this node and that node, simplify and see what you get. You will see that VL2 has to be 0. Okay, all right, so we found the response to I2. And that's 0. We need to find the response to V1, and then we're done. So let's go ahead and do that. I have to, let's see, maybe I'll go back here, erase something, because I don't want to carry this over to the next page. So I will try to erase this example here. And now I can solve that circuit here. So we want to set I2 and I1 to 0. And we want to keep only V1, right? That's the third independent source that we have in the circuit. Okay, so let's go ahead and do that. So now we say keep V1. All right, so we want to keep this and want to set these two to 0. This is 0, it's an open circuit. This is 0, it's an open circuit. They're gone. These branches no longer exist. All we have is this, and these two resistors. So here's the circuit that we have, a nice little voltage source called V1. Then we have a resistor on this side, R1, and then R2, and then R3, and R4. Okay, and again, this is the quantity of interest, and this time we'll call it Vout3. So our job is to find Vout3 in terms of V1. All right. Well, again, we have to see how we can solve the circuit. You can definitely write node analysis or mesh or something. If it's node, then this will be a super node. It's just to merge into one. It's not that hard to do that. Or we can try to see if we have any intuitive simplification. Not that easy to, it's not that easy to simplify the circuit. We could try to simplify it, but doesn't really help us much. We see that these two are in series and they're in parallel with this one. We could try to simplify, but we might as well just write some equations. So let's see. Okay, so why don't we merge these two into a supernode here. And we call that voltage VA. So we call this VA. If this is VA, then this is V1 less than that, right? Because we're going from high potential to low potential. So this voltage here is already known. It's VA minus V1. Remember, in the presence of a supernode, we had to write a KVL. That's what I really wrote just now. It's a KVL, right? Okay, so what we do is we say we are looking for VA and V out 3. Eventually, we're just interested in V out 3. But let's go ahead and analyze. Let's write a KCL at this node. So the current here going through R3 is VA minus V out 3 divided by R3. So that current is VA minus V out 3 divided by R3. This current is easy. That's V out 3 over R4. So then I can write a KCL here without any trouble. So let's write two KCLs. The first one is this current is equal to that current. So that's VA minus V out 3 over R3 is equal to V out 3 over R4. Okay, that's one simple KCL that we wrote. Now for the supernode, we also have to write a KCL. So that means that we take this box and identify all the currents going into it or coming out of it and sum them up. All right, so how much is this current here coming out? It's VA over R3. So let me try to put that right here, VA over R3. Going down. And how much is this current here? So it's getting really crowded here. Let me change the color of my pen. Okay, how much is that current? This current here, going from top to bottom. Well, this voltage minus this voltage divided by this resistor, right? How much is this voltage? It's VA minus V1. So we have VA minus V1 over R1. That's this current. So this little blue box has 3 branches, and we have to add up all these 3 currents. So our next KCL will be, this is coming out, so we have a VA minus V1 over R1. This one is coming out, so plus VA over R3. And then this one is also coming out, that's VA minus V out 3 divided by, sorry, this should be R2. Should be R2, this should be R2, this is R3. Okay, and all of these have to add up to 0. So now we have 2 KCLs and 2 unknowns, V out 3 and VA. We can find both of them. We can find V out 3. And the final total voltage that we have here, resulting from all these 3 sources, would be the sum of those 3. So we say V out total is equal to V out 1, which we found to be this. So that's V out 1 plus V out 2, which was 0. We saw that here. And then plus V out 3, which we get by this analysis. Okay, so you see, these are the mechanics of superposition in order to analyze the circuit. Again, you might ask, is this really simpler than treating the circuit with what we know before, like node analysis, right? Can I just write node analysis here? Yes, and in fact, that might be even a little faster than what we did here. We would have a super node here, and we would have only one voltage here, one voltage here. So that would be actually similar to the work that we did in this last part. So whether superposition is helpful or not depends on the actual circuit we are dealing with, but it's a very nice tool to have in our library of techniques. Okay, all right, so it seems that we are approaching the end of our lecture, so I may not have enough time to talk about Thevenin's theorem, but let's start out, and the next time we will come back and revisit. So Thevenin's theorem. So Thevenin's theorem is a principle that allows us to simplify a big chunk of a circuit. And here's how it goes. Suppose I have two pieces of a circuit that are connected by only two wires, so A and B. So any of the circuits that we have analyzed so far, right, you can just always stretch the circuit so that you have one piece here, and there are only two wires connecting these two pieces. All right? Okay, so Thevenin says that for each of these, you can create a much simpler equivalent circuit. So Thevenin says that I can replace this whole thing with a simple model. So in fact, it will be like this. It will be a voltage source, which we call VT, T for Thevenin, and a resistor we call RT, Thevenin resistance. And this is the entire A. And then if you want to connect it to B, sure, we connect it to B. Okay? So here are the conditions that you have to keep in mind. A and B are connected by only two wires. No fewer, no more. Two wires. And condition number two, we can simplify A to a single voltage source and a single resistor connected like so, still having two wires coming out. So in other words, this part of circuit B doesn't feel the difference if I take this entire complicated circuit and replace it by one voltage source and one resistor in series having two wires coming out. All right, that's the beauty of it. Of course, you can do the same thing for B if you want, but in any case, that's the basic idea. So the only question is, how do I find this voltage and how do I find this resistor, which together represent whatever the circuit does, right? The circuit could have dependent sources, independent sources, various devices, etc. It can be pretty complicated, and we need a procedure so that we can calculate VT and RT for any given circuit that has only two wires coming out of it. All right, so that's the procedure that we need to show. And that's something that we will talk about next time. Next time we will see it's actually pretty easy how we find this voltage, how we find this resistor, so that we can take this complex part of a circuit and replace it by something simpler. I will see you next time.